Okay, so today's video is going to be about quantum mechanics. What am I doing? Quantum mechanics, but this is not appropriate color to use here. But it will be a relativistic, rela- relativistic equation. So we'll be talking about Klein-Gordon equation of quantum mechanics. So first of all, let's discuss about relativity, the the one which Albert Einstein introduced to us, relativistic theory. So let's get started with intro of relativity. In relativity, we compare everything with speed of light, speed of light, of light. So what we'll be talking about, which is 3 times 10 to the power 8 meter per second. What we'll be talking about here is that the frame of reference is different observation, observation. Okay, in the every different frame we have different weighing point, and so if we add that, now that we know about the relativity, that's the different observations are done. Every frame of reference has different viewing points. What that event, the event which is happening, is different for each frame of reference with different speed, velocity, which is less than speed of light. It can never reach it. Okay, so now let's talk about Klein-Gordon equation. Klein-Gordon equation. Okay, first of all, why am I choosing worse colors? First of all, we know about p momentum and mc square, right? Or momentum and energy. And when we like expand it, we get p and mc square. This can be a further increased to px square, px and py and pz. P is momentum and mc square is what is known as the a equal mc square. This can also be written as mc square equal to e over c square px square plus py square plus pz square. This is mass shell. Mass shell. What was mass shell? We have talked about it. Anything in this universe, it must satisfy mass shell, and the humans are the best example of mass shell. High mass. Condition must have mass, momentum, energy, and I think the last one was time, if I'm right. So this is mass shell. This was we all talking about mass shell. Now let's get to the quantum mechanics part to derive Schrödinger equation. First of all, energy operator. This is I h bar d over dt. Okay, this is not d. This is partial derivative. Partial derivative, and then we have p equal m. Sorry, p equal I h bar d of dx. Okay, this can also be written as I h bar d of dx d of dy d partial d of partial dz, if we are talking about all the directions of momentum. And energy is mc square equals to E over c square, E over c square, or it becomes I h over c square d of t, sorry, d of dt square square part of what we have square. Am I missing E? Nah, no need. C's, we don't need to require C. Square. Okay. So then when we combine E and P, energy and momentum operators, we should get I h bar over c square d square over dt square minus this one, yeah, minus my, by the way, I will go out because minus I square is same as saying 1, and I will not go to the mathematics of that because simple. Minus h bar over c square d over dt square, and wait, what, oh sorry, why am I doing this? Sorry, so sorry. And over here, this is, let's remove this because it's the energy operator, not the momentum operator. D over dx, d over dy, d over dz. Okay, now if I shift this over to that side, I should get I h over c square d square over dt square equals to, no, not equal, I'm shifting it, minus d over dx d of y and d of dz. Square. Wait, why didn't I add d? D of z square. And I can then equal to 0. Here I will just h is not required here. So then h bar is required, damn it. If I add this h in all of them, it will be a messy one. So what I will do is that, because it should be like this, h is required in all of them because we are separating it. So what will happen is, let's simplify this equation. Simplifying this equation will give us, what will give it, what will it give us? E equal mc square, and then or c square d square over dt square minus h bar d square over dx h bar d square partial, sorry, I'm saying d because it's a lot, but so I'll say it's actually d partial d. So let's combine. We'll just remove h bar from the equation, and we will get, because h bar, there are a lot of h bars, so let's remove them, and we get e over, sorry, not e, 1 over c square d square over dt square minus d square over dx square d square over dy square d square over d partial d square, and this gives us plus 1 over mc square over h bar. C should be ignored. Then equal to 0. This equals 0. Then let's simplify this to get this whole thing, no, not this whole thing, this thing can be written as 1 over c square of this. This is called Laplacian or I just call it a gradient operator. That's what I call it, gradient operator, minus this whole thing minus d square over d of x square d square over dy square and d square over dz square plus mc over h bar. This whole thing then can be written as, this whole thing can be written, will be written with the wave function, because we're talking about operators and operators must have wave function. And then simplifying this whole thing, this whole thing and this whole thing, this can be written as this plus this is written as mc over h bar is what we call this square sheet of equal to 0. And here we have our Klein-Gordon equation. Klein-Gordon equation. Okay, let's do an overview. So in the overview, what we will talk about, I will start from the Klein-Gordon, where I drive the Klein-Gordon equation. We have the two operators, energy operator and momentum operator, and what the equations are like, and then I expanded momentum operator into its parts because I was talking about direction. This was x, y, z in all directions. Then again combined mc square with the energy operator, because you can say I wrote energy as E equal mc square. So I expanded it. I got mc square equal I h bar over c square. This is what it looked like. And then I square, okay fine, I'll just write I square as well, what it means, okay, later. E and P, so, and the momentum operator and energy operator combined to give I h bar over c square d square over dt square. This is a partial time derivative, second partial derivative, and then again it's just, we can say, if I combine this, or if I like make a relationship between the equations, 1 over c square and 1 over c square minus d square over dx square, d square over dy square, d square over dz square plus mc square over h bar psi. It's this equation is the relativistic version of Schrödinger equation. This is what Schrödinger equation looks like: p square over 2m, wait, it's not the same complex version. Minus I is gone, sorry. Minus h bar square over 2m and d square over dx square. This can also be 4. This is non-relativistic, we are not talking about direction. Plus v of x square, and this whole thing can be written as x and t. We'll just talk about x1 equal to I h bar d over dt. Comparison is that this one is a relativistic, this one is a non-relativistic, that this one is used for spin 0 particle, relativistic particle. Thank you.